I have a string attached between these two bars from here to here. This is an elastic string. It's painted black and white. I put the cardboard back behind so that hopefully you can see it better. Notice that when I pull the string down and let it go, the string bounces back up and forth at a regular frequency. This frequency is called the fundamental frequency. This is the resonant frequency that this string wants to vibrate at. Resonant frequencies are dependent upon things like how long the string is and how tight the string is pulled. If I pulled the string tighter, it would want to bounce back up and down faster because the speed of the wave on the string is faster. I can also force this string to vibrate at its fundamental frequency if I can drive the exact frequency wave from this wave driver on the right end of the string. I have this wave driver plugged into a frequency generator on the back side, and if I adjust the frequency generator to the right frequency, then I can get it to vibrate at its fundamental frequency. Okay? I've previously determined that that fundamental frequency must be somewhere around 4.5 hertz. And you can see that if I drive this going up and down 4.5 times per second, the string vibrates up and down as though I had just pulled it and plucked it. Now this is where the really cool stuff happens. Right now, I'm driving this 4.5 times per second, which, as I said, is about the resonant frequency of this string. But notice what happens if I drive it at 2 times the resonant frequency, or at 9 hertz. At 9 hertz, now you can see I have 2 places where the wave is very high. One here and one here. Those are called antinodes. And I also have a place in the middle where the wave is really low, or it's almost dead. That's called a node. And in fact, I have nodes on the ends as well. This is called the second harmonic because it's 2 times the fundamental frequency. That is also a resonant frequency of this string. It's just not the fundamental resonant frequency. What do you think happens if I drive it at 3 times the resonant frequency, or approximately 13.5 hertz? I do that, I'm able to get 3 antinodes on this string. This is called the third harmonic. One way of recognizing the harmonics on a string like this is that you can count the number of antinodes, and that's the number of the harmonic. So the relationship between the harmonics and the fundamental frequency is very simple. Whatever the fundamental frequency is, you can find a harmonic by taking that fundamental resonant frequency and multiplying it by 2, or by 3, or by 4, or by 10. If I adjust this up to 10 times the fundamental frequency, I should technically get one that has 10 antinodes on it. This wave is at 45 hertz. And if I slowly adjust it, I can match the exact right frequency to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the 10th harmonic. This is truly awesome. I'm going to bring the camera nearby so you can see this better. You can see why this is called a standing wave. It's called a standing wave because it looks like it's standing still. It's actually kind of interesting. I think with the camera, you're probably going to see it flickering a little bit more because the frame rate of the camera picks it up. But if you were in the classroom seeing this live, it would just look like a blur. This is called a standing wave. And standing waves are the fundamental basis behind all musical instruments. This particular example shows a stringed instrument.